Yes, good morning, good evening. I hope everyone is doing fine and enjoying ITC so far. This is our third plenary session. In this plenary session, we'll be having one keynote talk, one visionary talk, and some announcements in between. I'm sure you'll be excited with all of that, and we'll go ahead and start with the first part. Again, welcoming you all to this third plenary. I would like to introduce our first speaker. Our keynote speaker today is Rob Aitken, a very good friend to many of us, who has been in the field for a considerable amount of time. As you see, he is with ARM. He's a fellow of ARM. He's a technology lead there, and he performs research. Before ARM, Rob has been with Artisan, with Agilent, and HP. I'm going backwards. And he has graduated from McGill University with his PhD and University of Victoria with his master's. Rob is also familiar to ITC very well. He has been the program chair, the general chair, and he has a very interesting talk to share with us. By knowing ITC so well, he will tell us what's now. Okay, and I leave the podium to Rob.
All right, thank you, Yervant. Let's move into the slides here. So thanks for inviting me. It's a shame that we can't be in Washington all together to see each other, and but it's exciting to be at the first virtual ITC. So the question of the day is 50 years of ITC, now what? If you look at the motto for ITC, it's enabling the modern world, and that's a good place to start. So 50 years ago in Cherry Hill, New Jersey, the precursor to ITC happened, and it started to talk about memory chips like this one, the Intel 1103. The location of that has now apparently turned into a Mercedes dealership, according to Wikipedia. But in any case, they had their meeting and they talked about test. In 1970, I wasn't really talking about test very much. I got into it a few years after that, as Yervant mentioned. So what's been going on over those years? I made a word cloud out of the ITC 91 program, which was essentially 30 years ago. And the reason for that is it's the earliest one that I could find where it was in text and I didn't have to actually create this on the fly. But in any case, you take a look at that and then you take a look at the word cloud for today, and you can see that they're actually quite similar. Test is obviously number one. In 2020, there's more of an emphasis on learning and diagnosis. In 1991, it was more of an emphasis on circuits and faults. But nonetheless, the topics are the same, and even some of the people, if you look really closely, are the same. You can see Yervant in there someplace, for example. 1991 was also the year, it was the one and only year when my son RJ attended ITC, and you might remember him if you were on the boat cruise way back then, because he made his presence known. And for completeness sake, here's what he looks like today with his wife there. So moving forwards, let's take a look at why you might want to listen to me or not. So at ITC 2000, I gave a talk, and in this talk, there were 4 specific predictions that I could find, at least reviewing it. I've listed them here, and let's take a look at my track record. Did I actually predict things correctly? So DFT circuitry will be fully integrated into design flow. Did that happen? Yep. Wires matter, especially IR drop and resistance. Is that true? Yes. We need better correlation between timing tests and functional failures. Yeah, that was true then. It's still true now. It's still a challenge. So I wouldn't give it a full yes, but let's give it yes, but remains challenging. And then I was advocating more complex modeling of defects to predict their behavior. Did that happen? Not really. Instead, what happened is people started looking more closely at the relationship between test conditions and the data that came out of test. And there's lots of stuff at ITC on that, and we'll talk some more about it. So should you listen to me? Maybe, mixed bag. Anyway, here we are. Let's continue. I would argue that the reason that ITC has been successful over all these years is that we've followed some very, very simple ideas that turn out to be quite powerful when they're used together. So I've listed 3 of them here: Stuccat faults, scan, and logic synthesis. And I think all of these 3 have been key to ITC's success over this long period of time. If you want to know the story of that mug, you can reference or send me a message. It's, I believe, one of only 2 in existence. Okay, so simplicity and Stuccat fault. Simplicity, again, is the key idea that we're having here. And I have not always been a fan of the Stuccat model. There's a little bit of dispute over the origin of it, but let's go back to 1962 in this paper by Seshu and Freeman, and you can see that it's clearly in use in 1962, so predating ITC by at least 8 years. Now, why has the Stuccat model been so successful? I think it's a combination of these 6 factors. So Stuccat faults are local. They affect individual parts of a circuit, which mimics what defects do. Defects are physically local, but collectively they're global. Collectively they span the entire design, and that's also important because without spanning every place that a defect could happen, you're not going to test anything. They're logical, so you can use a conventional simulator for them. You don't need circuit simulation or SPICE. That also makes them tractable, which means that we can deal with them very large circuits, and they adapt. So the circuits that Seshu et al. Were looking at in 1962 are very different from the ones that we're looking at ITC today, but nonetheless, the same model works just fine. And they scale, and so that's really a key point that we'll return to. So again, simplicity is a function of scale. So if I have some rocks in my yard and I want to move them, a wheelbarrow and a shovel is a simple and perfectly usable method of doing so. On the other hand, if I had a much bigger pile of rocks, then I should get myself some excavators and some dump trucks and move that. Or if I have mountain scale levels of rocks to move, excavators and dump trucks aren't going to cut it either. And when you think about 50 years worth of Moore's Law, that's approximately 25 Moore's Law generations, or a 32 million roughly increase in size and complexity. That gives you, really, it's going from wheelbarrow scale to mountain scale. And yet our models and our methods have been able to move across that gap, basically, over that many years. Part of that is the simplicity of abstraction. So I think I'm going to argue that standard cells are one of the most successful abstractions in our industry's history. And the reason for that is they hide the fact that digital circuits are not digital. They're fundamentally a bunch of analog transistors, but by grouping them together in the right way, we can make them behave digitally. Now, if you take a look at the circuit diagram there, that's a flip-flop from the 90s. It would fail as a standard cell today because it has a bunch of features that are just really bad by today's standards. So that in signal, if there's coupling on it, that flop can actually latch. Process variation or weak drivers will break it. And the transmission gates lead to some strange fault behavior. So a fault at location 1 can actually propagate backwards out of the input and then cause untold damage elsewhere. So the upshot of this is if you want billions of transistors, you really ought not to build them this way. So abstractions need to be simple, but they also need to cover whatever level of scale we happen to be at. So this worked 10 Moore's Law generations ago. It does not work now. There are a few ideas, again, from sort of 25 years ago that were important then, and we had a lot of papers and talks about, but they've gone by the wayside, and I'm going to argue that they became too complicated to design at scale. So partial scan is one of those. An example story, back in the 90s, we were working on a chip, and the chip team wanted to use partial scan. They said, can we use partial scan? We want to save some area. And we argued, Peter Maxwell was involved in this discussion as well. We argued at the time that if they did that, it was going to add 2 months to the chip schedule. And they looked at that and they said, oh, 2 months, that means we miss Christmas with this product, so let's not do that. They just went full scan. And that shows you the power of simplicity, that partial scan, even though it's advantageous in area, it's too complicated to implement at scale. Now, none of these things went away. Partial scan still exists in parts of our design, as do tri-state buses, bidirectional wires, asynchronous, etc., but they've been really squeezed down. They're hidden away in places away from the mainstream part of the digital circuitry. Flying cars are a similar thing. They're just too complicated to survive. They're not good as cars or airplanes, and so that they, again, probably are going nowhere. If we were in Washington, you could go see this particular flying car at the Air and Space Museum. And for those of you watching in Washington, I guess you probably can go do that too. But the rest of us will have to wait until some point in the future when we're allowed to travel again. All of that brings us to an idea that was expressed very well by Einstein, I think. Make everything as simple as possible, but not simpler. And that not simpler part is really key. Some of the partial scan, et cetera, were just not simple enough. On the other hand, there are various forms of complexity that we're just stuck with. We haven't been able to abstract them away. So interestingly, I was able to reuse a couple of slides from my talk at ITC 2000. So let's take a look at one. So here's one where I was talking about clock coverage. And the white line in the picture represents the clock network in this particular chip. So clocks were complicated in 20 years ago. They're still complicated now. There's better ways to deal with them in the tools than there used to be, but nonetheless, the problems still exist. Power delivery is another one that has plagued us for many years. It was starting to be a problem in the 90s. It's continuing to get challenged. And it's a complexity that we're not going to be able to get rid of, because power, not just power delivery, but power switching, power islands, communication across them is a key part of our designs these days. Interfaces of various points are still there. They're where abstraction levels collide. So the interface between logic and memory, for example, the memory abstraction, the logic abstraction are slightly different. Interfaces between blocks, interfaces at chip boundaries, etc. A lot of that complexity is due to analog circuitry, which again will always be with us, I think. To make this concept a little bit more concrete, I thought I would give you the story of Razor. So Razor was a method developed at the University of Michigan, and it was designed to shave margins, get it? And get chips to run faster. At ARM, we spent about a decade on this, and here's how it works. So the idea is to exploit the dynamic nature of variations by overclocking the design. So you run the design faster than the margins would allow. You use a transition detector like the one shown in the figure to check for late arriving signals. And if there's a timing error that you observe, you don't just say, oh, an error happened. What you do is you actually invoke a recovery mechanism, which in a processor is a pipeline flush. That allows you to restart, redo the calculation at a lower frequency or higher voltage, and resume without an actual error. So you target the design to have a close to but slightly above zero error rate operation. That lets you survive fast-moving changes like IR drop, etc., and adapt to slower moving or static conditions such as temperature, aging, etc. So that's a pretty cool idea. Did it work? Yes, it really did. Here's an example. This is some actual silicon data from a chip. You can see when it's doing nothing, it's able to cruise along at 1.2 gigahertz. That drops down to a gigahertz when it gets the power virus workload. When the power virus workload goes away, it pops back up to sort of 1.1 gigahertz range. So even though timing errors are happening, the chip is still running correctly. So that's cool. Technology works. But why isn't it everywhere? The reason is really its lack of simplicity. So even though it was able to improve performance and yield, it's really hard to do in practice. It's hard to retrofit a microarchitecture, and the parts of the microarchitecture that cannot be razorized are really hard to design as well and make them robust. So essentially, the technology was cool, but it wasn't simple enough to be used. Okay, just another quick aside here, if you want to read this paper by Leon Jean. if you use razor-like circuitry, but you don't let the design fail, that makes it slightly simpler. So again, feel free to read that if you want. Okay, that brings us to ITC 2020. What are the challenges that we're facing? Machine learning, AI, analog, diagnosis, all of these things. You've seen papers throughout the conference on them. They are big problems and big challenges that we're looking at the moment. Okay, terrific. This talk was called 50 Years of ITC. Now what? So now what? What are we going to do about any of these things? So let's look at a few possibilities and move forward. Before we do, implicit in all of the challenges and in our responses so far has been Moore's law. So we can argue about when or if it will stop, but it's clearly slowing down. And the options going forward fall into three broad categories. There's more, which is essentially more of the same, better devices like nanowires or complementary FETs. More than more, which is stacked die or different materials, 3, 5, etc. And then there's beyond more, where we just give up on CMOS entirely and go for different logic designs, spintronics, memristors, and so on. All of these are options going forward. The actual path forward will be some combination of them. So let's look at emerging devices as a starting point. So we talk about emerging devices. We've been talking about them for a long time. When are they going to actually emerge? In memory, they're starting to happen already. You can buy MRAMs and so on. But what about in logic? So here's a quote from an anonymous research fab engineer that I liked. He said that the post-CMOS logic device options ranged from wildly improbable to impossible. Effectively, that means that the devices are going to emerge in some kind of niche application where regular CMOS isn't really going to work. None of these things are going to overthrow CMOS in the next decade, but after 2030, the odds get better. So that's good. What else? Well, there's data. There's a lot of talk about data at ITC. And what I've observed and what you may have observed is that the data story tends to be the same, whether it's in test or not. So the starting point is we need some more data. Oh, now we have lots of data. Lots of data. Terrific. Oops, now we have too much data. But we can use machine learning to deal with our data problem. Oh, but now we have to understand machine learning. So we wind up at the point where we need to analyze the data properly. And you can see actually from the Google Trends that this is it's a global effect. So the blue line, big data, rises rapidly and then starts fading as people figure out what to do with data. Machine learning rises rapidly or rises slightly more slowly and peaks, but analytics plods along and increases over time. So that's effectively the key here, is that we get some data, we can use machine learning, but analytics is really the key to understanding it and to making sense of it. So Scott Davidson in his blog mentioned that machine learning is everywhere at ITC. You've seen some good talks on it, I have as well. Let's look at two broad categories. The first one is testing ML processors. Really, that's not that much different from testing other digital processors, especially GPUs. So again, that's not really the key research concern. Instead, the concern revolves around using machine learning in test. And there's two ways of approaching this. One is to take an existing process and automate it, where effectively the training exists already. We know what good is, we know what bad is, and move forward. Working on untrained data is more challenging. Again, there have been several papers on this at ITC. Jenny Zheng had one on it yesterday. Take a look at her paper if you haven't already. But I'm going to argue that what we really need, because as test people, we want to be able to explain why something happened. We're dealing with a black box is challenging. So we need more explainable AI. And what that effectively will do is allow us to move this curve where existing interpretable models tend to be less accurate. We want to move that whole curve to the right. We want to improve the interpretability of the results without sacrificing accuracy. So I would say going forward, this is a key challenge. This is something that we need to think about as a community. There's also the future of security. Security could be really its own talk. This entire talk could have been on security. And I will get one at Host next month, plug. But let's take a quick look at where we're at. And I'm going to argue that hardware security is roughly where DFT was 25 years ago. So what I mean by that is everyone agrees we need it, but we're worried about what it costs and we're worried about what it covers. So there's thought and work that needs to go in there. It needs to be a full participant in the hardware design process, but also in the integration of that hardware with the software stacks that sit above it. It needs to be integrated with DFT, especially in and around lifecycle management, because you have the DFT circuitry provides both a means of configuring the chip as well as a attack vector. So some thought around that is important. And in all of this, standards can help. So if we all agree that certain security properties are valuable or that certain methods of providing that security are good, then we can start to compare and go establish the coverage capabilities and cost metrics that we like. So PSA is an example of a standardization approach, and there's others out there as well. Another area that could easily be its own talk and is in fact its own workshop at ITC is 3D. So tall is the new small. As of the various beyond more options, 3D I think is the most promising. But our challenge is that as an industry, we're wired for 2D. And what I mean by that is we think in block diagrams. When you think about how to put a chip together, you think, well, this one's going to talk to that one and so on. The tools are designed around 2D implementation. They have 3D versions, but the fundamental thought process again is 2D. Luckily for us, existing 3D designs are not really 3D. They're stacks of 2D things. And what I mean by that is there's limited freedom to make vertical connections. I can't connect something over here to something over there without going flat on a different layer. So true 3D, when it shows up, is going to create some opportunities that we don't grasp yet. But it also leads us to some interesting challenges. So remember that the key to things being successful is they need to be simple enough, but not too simple. So let's take a look at some things that are simple enough. So we can make inter-die connections. So here's an example. There's a figure over there from an ARM Global Foundries test chip. And we built this thing, and it has around 3,000 connections that go back and forth between the die. They operate at speed. And at the time, they incorporated P1838. So you notice the P is still there in the diagram. Stacked memory on logic is also something that I think is simple enough going forward. And heterogeneous stacks are going to work as well, but not simple. Heat transfer is not simple. Power delivery is not simple. Inter-die margining and managing supply chains across companies. All of these things are still really, really difficult in 3D design. And that means that the kind of super chips that were envisioned at IEDM 2013, and you can see in this picture, these are still a ways away. They're not going to happen anytime soon because they're just too hard to build. There are some interesting anomalies in 3D design as well. And I thought I'd show you this one because I find it kind of amusing. So taller isn't necessarily taller. So an HBM2 thickness, 6 die, 720 microns or micrometers. The single 300 millimeter logic die is typically 775. So that's slightly taller. 1 die is slightly taller than 6 die. And you can see it in the picture from Kyocera over there. It's not an accident that that memory chip is slightly under the logic chip. The reason for that is that the logic chip generates a lot of heat, and you want to be able to make good thermal contact right to the surface of that logic die, which means you can't have the HBM die getting in the way. Heat I think really turns out to be the biggest problem. It's the biggest problem I can think of in 3D space. So we can cool a stack of die comparably to a single die. But if we're going to move past Morse type scaling, we'll need to do better than that. We'll need to be able to find a way to cool multiple die as effectively as if they were multiple single die. So there's some ideas out there. You can see a couple of them here that I pulled out of the Journal of Heat and Mass Transfer. I bet you didn't know that journal existed, did you? But in any case, you can see they've got some liquid flow. They've got some, effectively, if you look at the water flow or the coolant flow through these things, it's pumping coolant at roughly the same rate that you pump it through a car radiator. And that allows them, in the bottom paper, they were able to dissipate 500 watts per centimeter squared. So that kind of solution is able to dissipate the amount of heat that we want. But is it simple enough to exist? And that I think is the key question to some of these exotic techniques. Where is the simplicity boundary? And there's a bonus question of how exactly do you test for heat? If the thing has a heat spec, how do you know that it meets it or doesn't meet it? And again, we have solutions out there that we use, but are they the right ones going forward? Okay, so all that, we've had a bunch of discussions. What's the point of all of this? Where is ITC going? Now what? How do we enable the next 50 years? I've argued that ITC has been successful because we've made tests simple, but not too simple. And we can apply this principle to the future technologies and see which ones are more or less likely to succeed. And I showed you kind of examples of how to do that with AI and with the heat generation and so on. So all of that brings us to, I think ITC has a big future. There will be plenty of material to keep us all busy for a long time forwards. I have no particular plans to attend ITC 2070, but I do hope it goes well. And I will conclude with this picture that I took at the very first ITC that I attended back at the Marriott, when it wasn't the Marriott. And talk to you all later. Thank you.
Oops. Thank you so much. Thanks, Rob. This was very eye-opener, very nice question. In the interest of time, we'll take one question, maybe.
Okay.
The question for Rob comes from Sagar Sabade. He's saying, whose responsibility is it to manage security? Test or DFT in general and security often had orthogonal goals. How do you see it's evolving and moving forward? So I guess two questions embedded together.
That's an excellent question, and I think it's really the key to success and the key reason why standards are important. Because testing is important, DFT is important, because we want to make sure that when we release a chip that it's defect free. But securities needs to exist throughout the entire lifetime of the design, which means that the primary benefit of it accrues to whoever it is who buys the system or builds the system that it eventually is part of. We also know that security needs to evolve over time. So we need to find a way for the end users of systems to specify the amount of security they want and then pay for that. Part of that means we need to be able to express coherently what more secure means, so that we're arguing for, you need to have this, rather than security's good, buy it, without any real technology behind it. So that's I think the key, is having some standards in both our terminology and our metrics, so that we can have a sensible discussion about why someone should manage it and pay for it.
Perfect. Very good. Thanks a lot, Rob. I appreciate it. Again, thank you for the great talk. We look forward to see you at many more ITCs.
Likewise, yeah.
Yeah, perfect. Okay, so what I'll do next is I have a few small announcements, and then we'll move to our visionary talk, okay? In terms of announcements, as you may know, ITC has started to do something different this year to encourage the exhibition floor. Since we are in the virtual mode, we'd like to go from the conference area to the exhibition and dig the information available to us. So we do have there 8 exhibitors, 12 booths total, that are participating in this drawing of iPads, okay? So there are 2 iPads per day that are provided. And here you see the different exhibitors that you may visit to be able to win those iPads. We started that process already yesterday, and we have 2 winners from yesterday. Samir Bubezari is the first winner from Qualcomm, and Soon Hong Tae is the second winner from Intel, each of which receives an iPad as a result of the drawing. Our general chair and program chair are contributing to the drawing process. It's a very nice way of encouraging and thanking our participants as they visit the exhibit's floor. Today we have again another opportunity for the drawing of 2 iPads, and any attendee will be eligible to do that, but except the 2 who have already won. Okay, so besides these 2 winners, reminding them of the rules. The person has to be a registered attendee, a full conference attendee of ITC. He or she must visit 4 exhibition companies, not the booth, because some companies have more than 1 booth. And they could repeat the same places that they visited yesterday. That is okay. And if you have any questions, of course, you can approach us. A reminder, that is, the exhibits will close today at 3:30 p.m. in Eastern time. Okay, so you have time until then. And after that, of course, we'll be happy to announce the winners and communicate with them with their gift. Now, there's something that I promised during the opening session, that we have our Best Doctoral Thesis Award named after Professor McCluskey. Many people participate in this at the doctoral stage, and we do the semifinals at different conferences, TTC conferences around the world, and we do the final selection at ITC. So yesterday we had that session of the final competition with the semifinalists coming and presenting their PhD work, with judges from industry, academia participating in the selection. And I'm pleased to announce who has won the end result of this award. So the end result is won by Muhammad Nasim Imtiaz Khan. He's from Pennsylvania State University. Congratulations, Muhammad. We are very pleased that you were able to participate, and also to be the Best Doctoral Thesis Awardee for this year. This work has been the best that was selected from VTS 2020 in this same competition, and his PhD thesis has the title Assuring Security and Reliability of Emerging Non-Volatile Memories. Again, congratulations, and looking forward to more winners in the future years. Another award that we also announced at this stage is our partnership with JETA, the publication. So it's the JETA TTTC Best Paper Award of the year. Typically, we look at the previous year, that is, in this case, 2019, and we select the best paper. There's a full process, a selection committee, judges, and so on. And this year, as you see, the winner is this paper, Test Flow Selection for Stacked Integrated Circuits. Okay, very timely topic on stacked integrated circuits, as Rob also was mentioning. And we have a workshop dedicated to that starting this evening. The winners are coming from 2 universities, Brita Sangupta, Dimitar Nikolov, and Eric Larson from Lund University, and Asmitra Dash from Linköping University, both in Sweden. Okay, again, congratulations on behalf of TTTC and Springer for this special award.